Welcome to This Explainer. Today, we're diving into the incredibly high-stakes mathematics of strategy, and we're going to see exactly how we can optimize our everyday interactions. I am so thrilled to guide you through this because honestly, once you understand the hidden math beneath our choices, it can profoundly change how you navigate the entire world. Okay, so here's our roadmap for today. We're going to cover the mathematics of strategy, the famous prisoner's dilemma, the ultimate computer tournament, the rules for actually winning at life, how to deal with uncertainty, and finally, living in a non-zero-sum world. 6 key stages, so let's jump right in. Section 1. The mathematics of strategy. Let's lay the groundwork and establish exactly what it is we mean when we use the word strategy. Now, we aren't talking about solo efforts where you are in total control. Think about running a mile for a $100 reward. Your success there depends entirely on your own sweat and effort, right? Instead, we're talking about strategic interactions. Think of a complex game of chess. In these scenarios, your opponent's choices directly influence your outcomes, and your moves have to constantly adapt to theirs. And that brings us to the formal definition. Game theory is essentially the study of decision-making under conditions of uncertainty over time, using mathematical models of strategic interactions. It was originally pioneered by the brilliant mathematician John von Neumann, and this framework is literally the ultimate tool for decoding human behavior, economics, and, believe it or not, even biological evolution. It gives us a way to figure out the absolute best moves when we aren't the only ones playing the game. Section 2, the prisoner's dilemma. Let's look at the ultimate Cold War game, which kicked off with literally the highest stakes imaginable. Picture this. It's September 1949. The United States discovers radioactive traces in the atmosphere. This proved, without a doubt, that the Soviet Union had successfully tested a nuclear bomb, effectively igniting the Cold War. The sudden loss of their nuclear monopoly forced the U.S. into a terrifying strategic interaction with the Soviets. It was an absolute existential crisis, one that the Rand Corporation tried to solve by actually inventing a game to model the conflict. Let's break down the math behind this famous setup, the prisoner's dilemma. Imagine if your opponent cooperates. You could get 3 coins by cooperating 2, but you'd get 5 by defecting and betraying them. Now, if your opponent defects, you get absolutely nothing, 0 coins for cooperating, but you salvage 1 coin by defecting. So, mathematically speaking, no matter what your opponent decides to do, your most rational choice to maximize your own gold coins is always to defect. And that terrifying logic perfectly explains why 2 rational nations would spend $10 trillion building massive arsenals of weapons that they could never actually use. To fully grasp how to escape mathematical traps like that, we need to quickly define a few academic terms, starting with a really crucial distinction. A zero-sum game is a scenario where one player's gain is exactly balanced by another player's equal loss. Basically, someone has to lose. But a non-zero-sum game? That's one where outcomes can result in net gains or net losses for both parties simultaneously. In these types of environments, mutual cooperation is actually mathematically possible. It's also super important to structure how a game is played. Simultaneous games require players to make their decisions at the exact same time without knowing the other person's action. That kind of keeps you guessing in the dark. In contrast, sequential games let players take turns. This is a game changer because it allows you to build a logical strategy based on the past moves of your opponent. Finally, we have to consider our visibility. Do we have perfect information? That's like a fully visible chessboard where every past move is completely known to everyone. Or do we have imperfect information, where certain moves, intentions, or details remain totally hidden from opponents, much like holding a secret hand of cards? All right, Section 3, the ultimate computer tournament. Let's see how scientists scaled these interactions way up to uncover the secrets of cooperation in the natural world. The real secret here is that life is rarely just a one-off event. Take the impala dilemma, for example. Out in the wild, impalas face a repeated game when choosing whether to spend their valuable energy grooming infectious ticks off of one another. The catch? They know they're going to see each other again tomorrow. Because biological organisms interact repeatedly over long periods of time, political scientist Robert Axelrod realized something huge. Playing the prisoner's dilemma over and over completely changes the math, simply because your opponent remembers what you did yesterday. To test this theory, Axelrod invited experts to submit coded strategies for a massive 200-round computer tournament. This resulted in a really fascinating cast of characters battling it out for the most points. You had Friedemann, a code that holds a permanent, completely unforgiving grudge after just a single defection. You had Joss, this sneaky strategy that copies moves but randomly defects 10% of the time. And then you had Tit for Tat, which simply cooperates on the very first move and then perfectly copies whatever the opponent did last. Section 4. Rules for winning life. This brings us to exactly which code completely conquered the tournament, and more importantly, how it applies to you. So, the wildly successful winner was actually the remarkably simple tit for tat code. By analyzing all that data, Axelrod proved that establishing a pattern of trust while flat out refusing to be a pushover is the ultimate evolutionary strategy. It basically boils down to 4 simple steps. 1. Be nice, meaning never be the first to defect. 2. Be forgiving, so don't hold long grudges. 3. Be retaliatory. Strike back immediately if you're betrayed. And 4. Be clear, making your strategy completely predictable and very easy to trust. But there is one tiny flaw we do have to adjust for, and that's the problem of noise. See, in the real world, accidental errors happen. For example, back in 1983, a Soviet satellite falsely detected a US missile launch. Now, if we strictly played tit for tat in that scenario, one sheer accident would trigger an endless echo of mutual retaliation. So, to survive real-world noise, game theorists found that you actually have to add about 10% more forgiveness to your strategy. Without a little extra grace for those accidental miscommunications, mutual destruction is practically guaranteed. Section 5. Dealing with uncertainty. Because successfully navigating life's miscommunications requires a really solid grasp on probability. As game theorists often point out, in any given poker situation, you're dealing with a whole lot of uncertainty. It's all about how to make the best decision in any given moment, and that is just so integral to life. In fact, John von Neumann based a massive amount of his game theory on a stripped-down version of poker, because he understood that life is rarely a game of perfect information. And this brings us to a frankly devastating mathematical and psychological trap, the sunk cost fallacy. Imagine you have a massive stack of chips in the middle of a poker table, but based on the cards in front of you, you are 85 to 90% confident you have the worst hand. You are losing. Yet, human nature constantly pushes us to refuse to fold, simply because of what we've already invested. So the crucial takeaway here is that we absolutely must use game theory to overcome those sunk costs and cut our losses. Sometimes that means finally putting down a book you just aren't enjoying after 100 pages. Other times it means walking away from a PhD program that's making you miserable. By acknowledging this fallacy and utilizing what's called a min and max strategy, which mathematically minimizes your maximum possible loss, you can objectively evaluate your life choices and pivot toward a better future, totally regardless of what you've already spent. Section 6, a non-zero-sum world. Let's tie all these incredible concepts back to the global stage. Decades after the Cold War began with that absolutely terrifying prisoner's dilemma we talked about, Reagan and Gorbachev actually utilized game theory to safely de-escalate through the START Treaty. They completely avoided a massive leap of blind trust by engineering a strict sequence of small, verifiable cooperative steps. They acknowledged the mutual benefit, broke the massive dilemma down into tiny, manageable interactions, eliminated just a few weapons at a time, and rigorously verified the opponent's compliance before ever proceeding to the next stage. And this reveals our ultimate takeaway. In a non-zero-sum environment, you do not need to extract your reward from the other player. You can actually both cooperate and extract your reward from the banker, which in this case is the world around us. The crucial point to remember is that so much of life is just not a zero-sum game. The math proves over and over that cooperation frequently pays massive dividends, even among bitter rivals. So as you step back out into a world filled with strategic interactions and profound uncertainty, I really want to leave you with this one provocative thought. In the games you play every single day, are you merely trying to defeat your opponent, or are you actively looking for the win-win? Keep that strategy in mind for your very next interaction. Thank you so much for joining me for this explainer.